How did you find assignment 4? Hard. Terrible. Okay, so it seems to be so assignment 4 compared to assignment 3. Okay, so I'm always confused by this because assignment 3 to me seems like the scary one, where you're given absolutely nothing and told to build a game. And assignment 4 to me felt like you were given a framework and there's a couple of lines of code you have to stick into each of those functions. And this has happened in previous years as well. Though usually I've tried to be more ambitious with assignment 4. People did, in the past, they did a whole music library where they had to handle searching and indexing a big pile of MP3 files. And I'm still not sure I understand where the difficulty is coming from. So, and the commonality always in assignment 4 in this course when I do it is there's some kind of other data that you have to deal with. So maybe an MP3 library, and how you deal with it is in different ways. So for example, in the MP3 assignments, there was a special library for reading the metadata from these files. Here you're using a CSV file. So what did you struggle with this assignment? Okay, so is it just getting started? Getting anything done? I mean, what could I have done to make this assignment easier? Yeah.
I had some difficulty with question 2. I know myself, I found on the first read through, it wasn't clear enough what I was supposed to do.
Okay.
I made an entire program and had read it through again and go back and whoops, I did the wrong kind of post.
Okay, so maybe clarity a little bit more in the question. Maybe more carefully thought out sample output, so you can figure out maybe from the examples what's the issue. Yeah, that's possible. One of the problems with changing the assignment each year means that I have to reword it, and then I come across these kinds of problems. Anything else? Yeah. Yeah, so assignment 4, it looks like the number of people who submitted was about the same. So basically the numbers went something like assignment 1, maybe 200 people submitted it. Assignment 2 was 160. Assignment 3 was again up to 200 or over, and then 160 for assignment 4. Which again still is strange for me. It's still surprising to me that more people made a game than did these four, or tried to even do these four things. I don't know yet what the results are like on the games. I don't have all the marks in, so maybe some people were just submitting placeholders and not really a full assignment. But yeah, that's at least the completion rate. The grades, I can make some stats for those. Probably next Monday, we'll sort of do a bunch of administrative stuff before the midterm, including a midterm review, and we'll look at the grades so far at that point. Yeah.
Is this for the midterm? Are we only having one? Or is there two midterms?
Just one. Why two?
Some classes have two.
Oh, yeah, no, just one.
Is it multiple choice?
Yep. It'll be, I don't know, maybe 25 multiple choice questions, something like that. Yeah.
I know I personally found some of the logic in nested for loops a wee bit iffy with what can and can't be called and like the inner post loop relative to the other loops.
Okay. I see. So if you're, so you have a big for loop that is the outer loop around the iterating through the lines, the rows in the file, and then maybe you're doing an inner loop, doing whatever. Yeah. So what is what? Okay. So maybe today some of that will get cleared up when we talk about scope, although it's more about what you can access between functions, but maybe it'll help clear some of that up. Any other suggestions or recommendations or comments? Yep.
Question 3 didn't have any skeleton code.
Oh, okay, that's my fault. Yeah, it's basically question 4 is an extension of question 3, so yeah. I think I saw a comment about that on the forum sometime last week as well. Okay, so today I want to go slowly, and what I want to do is go back and revisit some of the things that we've been doing, but that we've kind of really glossed over some really fundamental things that are happening kind of under the hood in Python and in every programming language. And these are issues of scope and memory and what I'll call equality versus identity. So let's start with just an example. All right, so let's make an array that contains 4 values. There it is. An array or a list containing the integers 1, 2, 3, and 4. Let's do that again. And let's say maybe so there's a list containing, so I have A is a list containing 1, 2, 3, and 4, and I have B is a list containing 1, 2, 3, and 4. So is A equal to B? So who thinks the answer is yes? Okay. And who thinks the answer is no? Okay. So there's about half the people think the answer is yes, about 1 person thinks the answer is no, and half minus 1 has no opinion or doesn't want to guess. And the answer is yes. So these two things, Python treats them as equal. And that makes sense, right? A is a list. It has length 4, and the values in the list in order are 1, 2, 3, and 4. B is a list that has length 4, and the values in the list are 1, 2, 3, and 4. So by any sort of reasonable measure, these two things are the same, or should be equal. Well, Python has in it a deeper test of what it means for things to be the same or equal, and that's the is operator. So, do you think A is B? I mean, we've sort of agreed that they're equal, and Python agrees with us. But are they the same thing? Are they identical? No. And indeed, Python agrees with us that these two things are not identical. So what do you think it means that they're not identical if they're equal? How could we somehow, what kind of test, if some of you are scientists here, experimentalists, or will be experimentalists, what kind of experiment could we perform to check that A and B are really two different things? Yeah. So it's probably the case that A and B somehow, those two lists are in different places in memory. And that's sort of something that we maybe think is what's the difference between those two things, because they're the same length, they contain the same elements, but they're different somehow. And so the conjecture is that maybe they're at two different places in memory. How can we test that? Yeah. Good. So that's a good experiment. We could perform an operation on one of them and see if that affects the other one. And if they're really the same thing, then the operation on one of them should actually affect the other one. So let's see. And luckily, lists are nice. We can actually do operations to lists that change them, right? Here's A, and I can say A at position 1. I'll change that to be the string 2. I look at A, and I see indeed, now it has been modified so that the element at index 1 is the string 2. Did that change B? No. Okay? So somehow A and B really are two different things. So let's start over again. A is 1, 2, 3, 4, and B is A. There's A, and there's B. So, are A and B equal? Well, they should be, according to everything we think we understand. Are A and B identical? Are they the same thing now? Some of you say yes. Yeah. I said B equal to A, and so we somehow think that that means that they should be identical. And we can ask that. A is B. Now it's telling us that that's true. So it's somehow telling us that actually A and B refer to the same thing in memory. And we can test that again by changing one of the values in A. There, we've changed it, and it's also changed in B. That's because, in this case, A and B both refer to the same things in memory. So the difference in those two examples is, in the first case, I created a new list containing 1, 2, 3, and 4, and I assigned that to A. And then I created another list containing 1, 2, 3, and 4, and I assigned that to B. And those two things were two different lists. In the second example, I created A, and then I just said B, well, that's equal to A. So to really understand what's happening here, or the best way to visualize it, is with the help of some pictures. And that's why I've got this overhead camera up. And so what's really happening is, well, in the first case, I create a list that contains 1, 2, 3, and 4. And that list lives somewhere in memory, and that part of memory where the list lives, it has different names in different languages, but we call it, classically, it's called the heap. It's where you make things that come and go. And so that's what's on the right-hand side of this equality operator here. For example, I create that list. It creates it over on the heap. And over here, on this other side, which keeps track of my local variables, there's a variable which I'll think of as a little box called A. And what's stored in A is a reference to that thing off in memory. Okay? So when I say A equals 1, 2, 3, 4 like that, first this thing gets created off in memory, and then a little box called A says, okay, I now refer to this thing. And in this example, I said B equals A, and that creates a little box called B, and the contents of that box are given by the right-hand side of this equality, this equals operator, and they just come from whatever the contents of A was. Well, the contents of A was a reference to that thing. So now these two things refer to the same object over here in memory. Yeah. Well, a stack is a place where our variables, our local variables are going to go. And just think of those variables as little boxes, and the only thing you can do with a box is refer to something in memory. Okay. So I have two boxes with different names, A and B. So those are different boxes, but they happen to both refer to the same thing. Okay. So, and this is something we've completely sort of glossed over, the fact that things, the same thing in memory can have different names, but we've kind of been playing around with this, and it's important now that we really get a firm grip on what's happening here. So again, I'll reset A. A is now this new, this list in memory. And now I'll say B is equal to A, or B is equal to a slice of A, which starts at the beginning and goes all the way to the end. So now do you think A and B are the same thing? Do you think that they're identical? So this indexing operator that has all these, that in Python has all these cool things you can do, it's called the slice operator. It gives us a slice of A. Now, is that really A, or is it a copy of A? Well, let's find out. So A and B are equal, of course, because they're both two lists that contain the same thing. Are they the same thing? False. So that operator, when I say A at colon whatever, just creates a whole new copy of A, which starts at the beginning, because I never specified a beginning index, and goes all the way to the end, because I never specified an end index, creates a whole new copy of that thing, and then the box B refers to that thing. So they're different. And we can check, because we can modify one of the values in A, and that changes A, but it doesn't change B. Okay? So, any questions so far? All right, good. So let's try and write a function that takes a list A and sets all its values to 0. Or rather, let's even call that thing, let's call the list L. So how do we write a function like that? So someone gives me a list. I want to set all its values to 0. Yeah. Okay. So you iterate through the items in the list. So that's like for x in L, x equals 0. Okay, you've got it, but why not this? Why doesn't this work? I mean, we can test this and see if it works. So it doesn't work because I just called it on A and I didn't change the values at all. So what's happening in this code, right? This x takes on each value in the list, and then we set x to 0. Well, let's walk through it slowly and see if we can figure out what's happening. So we have our stack, we have our heap. So first thing we did was we created a list containing the values 1, 2, 3, and 4. And then we assigned that to a variable called A. So that's what that looks like. And then we called this function 0, and we passed it A as its argument. So 0 takes one argument. The name of the argument is L. Our variable is called A, but that doesn't matter. What does that do on the stack? That creates a new box called L. And the contents of L are the same as the contents of A. So that's what the picture looks like when this function starts to execute. And then what happens? What's the next thing I should add to this picture? Yep. Yeah. So here in this for loop, a variable called x gets introduced. Variables are just boxes. So that means it creates a new box called x. And x is the thing that's going to take on the values in A. So when we start, x refers to this value 1 here. Okay? And then the first thing I do is I set x equal to 0. What does that do? Well, that creates an integer 0 over on this side and says, well, now instead of x referring to this 1, it refers to this 0 over here. That doesn't affect A. It doesn't affect the contents of this list at all. It just changes the value in the box for x. And that's not what we want. What we wanted to change the value in the list over here. And then the loop executes once more. So that happens. We've set x to 0. The loop executes once more. And the second time through, x refers to this value 2. But again, we fail to overwrite it because all we do is we change the value of x to refer back to this 0 over here. And all that keeps happening is the only thing we keep changing is this contents of this box over here. And then finally, the function finishes executing. And all of this goes away. The function returns, and actually L and X disappear. So in the end, we've accomplished nothing. A still refers to the same array that it did before, and nothing has changed inside of it. So what we should have done, and the answer that was suggested when I started suggesting this one, is rather than iterate over the values in A, we iterate over the indices in A, which we get by taking a range which is equal to the length of the list so now I is going to take on the values 0, 1, 2, and 3 if I pass it a list of length 4. And what should I do? Yep. Yeah. Okay. So there I managed to write a function which takes a list as input and changes the values inside the list. It doesn't return a list. It actually changes the list that it's given. Let's write another function called zeroed. That returns a new list, the same length as L with only 0 entries. How do I do that? Yep. Between what? Okay, so in the first one, I give you a list. I give the function a list. The function returns nothing, but it changes the list. In the second one, and this happens, you see it all the time in the Python library, I give it a list. The function should not change the list. It should return me a new list that is the way that I want it. And in this case, I want a new list that has the same length, but all its entries are 0. So it shouldn't change the original list. So there's lots of ways to write this. Somebody want to suggest one? Yep. Okay, so I could say, let's call this thing L2. It's an empty list. And then iterate over the elements in L and say for each value x in L, I want to put the value 0 in L2. Oh, and let's not forget, the first word in the comment for the function says to return something, so we'd better return L2. Okay, so again, we start with a equals 1, 2, 3, 4. We call zeroed of a. And notice already that's different than when we called 0 of a. When we called 0 of a, nothing showed up because 0 of a doesn't return anything. This function, on the other hand, does return something. It returns a list, and it's a list that contains all zeros. It's this list L2. Okay. Any other ways we could have written that? So is there a shorter way to have written zeroed? Yeah. Yeah. So here we basically, this is the thing that list comprehensions were made for. We're going through every element in the original list, and we're creating a new list that somehow changes that value in some way. In this case, the change is really trivial, but you can write this as a one-liner. We return 0 for every value x that happens to be in L. So there's another implementation of the same thing. That also works. Okay. So these list comprehensions, they're another thing that create a new list. They don't modify the list that they're working on. And if you wanted a third way of doing it, would look like that. Remember, lists also support multiplication, so you can create a list of length 1 and then multiply it by which contains only 0 in it, and multiply it by the length of L, and you get a list of length 4 which contains all zeros. Nothing too exciting, just another way of showing you that there's always a lot of ways, different ways of doing things in Python. Okay, so is it clear what the difference between those two functions are? 0 and various versions of zeroed. So one of them changes the original list, the other one gives you a whole new list. And in Python you can find many examples like this. For example, lists have a sort method that you can call on a list that sorts the list. So nothing gets returned from it. All that happens is the values in the list get sorted. It also has a sorted function, which returns a new copy of the list, which is with its values in sorted order. Okay. And there's a bunch of examples, like that. All right. Questions so far? Yep. You should try and write programs, generally speaking, so that they're easy to read. Now, easy to read means different things to different people. People who are mathematicians or experienced Python programmers find this much easier to read than all of this. People who don't work in Python so much or don't have experience with these idioms can maybe step through this more easily than the other one. So for now, write it in a way that makes it easy for you to read and understand, but eventually know that, and some of you will have jobs at some point and people will say, oh, why did you write that for loop when you could have just used a list comprehension? In general, list comprehensions would be the preferable way to do it, but for now, do what you understand. Because, Okay? All right. So now I want to come back to another thing here, which we've kind of glossed over. So let's here I've defined a new function. And the concept is it computes the sum of the values in some list A. And indeed, it starts with this variable c set to 0. For every element x in A, it repeatedly sets c equal to its current value plus the value of x. So indeed, this should compute the sum of the values in the list A. The comment does what the comment says. Now, before I test it, does anyone see any issues? Any glaring issue with this function? Yeah? There's no return statement. On the other hand, the comment doesn't say that it returns the value, it just says that it computes it. So the comment is honest. It does indeed compute it. It really goes through and computes it, but doesn't return it. Now, does that matter to us? It computes it and it stores it in a variable called c. Can I get it? So let's take a look at this thing. What's the picture look like for this thing? We have our stack, and we have our heap. A is 1, 2, 3, 4. Fun of A. Doesn't return anything, as we expect. But the value is computed. It's in the variable c, right? Yes? No, c is not defined. So what just happened there? Well, I glossed over it on the previous picture, but here's what happens. First, we create the list A, or the list that has no name yet, 1, 2, 3, and 4 are its contents. We assign that to the box called A. And then we call a function called fun. And fun, so I'm going to just put this dotted line here. Fun takes an argument, which is called A. And so that creates another box called A that refers to the same thing here. And then the first thing fun does is it creates another box called C that refers to the integer 0. And then it starts iterating over the values in A using another variable called x. So initially, x starts out referring to 1, and we compute c plus x, so that's 0 plus 1, and we assign that to c. So 0 plus 1 is 1. That creates some integer 1 over here, maybe, and then we change c so that it now refers to that. Next time through the loop, x refers to 2. We add c, which refers to 1, and x, which refers to 2, gives us 3, and we assign that to the value c. Next time through, x is 3. We compute 3 plus 3 is 6, and we reassign the value of c to that thing. And then finally, x refers to 4. C refers to 6. We compute 6 plus 4 is 10. And we reassign that to the value C. So at the end of this process, by the time this for loop finishes, C is the value 10, which is 1 plus 2 plus 3 plus 4. And then the function returns. And what happens when a function returns? Well, what happens is all of the variables on the stack that were associated with that function, including its arguments and including any of the variables that I defined inside the function, so that's c, that's x, and even the argument a, they disappear. So all of this stuff, these three things, so I'll put in a little note here, that all of that belong to fun, the function, and once fun returns, all of that goes away. And then we're kicked back out here at the interpreter, and then when I ask for the value of c, well, the interpreter looks at all of the boxes that I have lying around, and none of them is named c, so it says c is undefined. So the things that you define inside a function and the arguments to that function, they only live as long as the function is executing. Okay. So let's drive that home. So here's a function. Fun2 takes an argument called a, and it sets a to 0. here I've defined a variable called A, which refers to a list 1, 2, 3, 4, and I call fun2 of A. What's going to happen? Well, we go through it slowly before we even do it. We know how this game starts. There's the stack, there's the heap. Start by making this list that contains 1, 2, 3, and 4. Over here on the box, we have, on the stack, we have a box called A that refers to that list. That's this line of code right here. And now what happens when I call fun2? What's that? Nothing that we won't observe anything, but what happens internally? Something executes. Maybe we don't see the results of it, but what is it? Well, fun2 executes, which means that it creates its own place to store its own variables, any of the variables that we define in it, and any of the arguments to it. One of the arguments to fun2 is called A. So there's another box called A created. It gets its value copied from the input argument, which also happens to be called A. And then this line of code says, well, we set A, our local variable called A, to 0. Well, all that does is say, this box here, instead of whatever used to be there, forget about it, and it should just refer to 0 now. And then that's it. The function is done. It returns, and when it returns, this thing goes away, and we're just left back with the same picture we started with. Oops. And if I ask about A, it's completely unchanged. It's not set to 0. Okay? So these things have, there's names for all of these things. So a variable, when it's defined, it has what's called a scope. And these variables here that I define, let's say, in the interpreter, as I've been doing, they have, let's say, what we'll call global scope. It means they'll always be around. When I call a function, it has these arguments, and it has these variables that get defined inside the function. Those things have local scope, which means that they're only around as long as that function is executing. Okay? So that's called the scope of a variable. It's how long the variable lives for, or where you can access it from. So that's just a name for that thing. So now we're really taking a peek under the hood here at what happens when we do this stuff in Python. And actually, I've just done like a good fraction of assignment 5 for you. So your best time to work on assignment 5 now would be to leave immediately after this class and go do the first 4 questions. So, any questions before we continue? Good. So it's always helpful to keep in mind that variables are just little boxes, and all they do is point to things. Okay? And when you set the value of a variable, meaning you put it on the left-hand side of an equality, of the equal sign, all you're doing is changing the contents of that box, making it refer to something else. Okay, good. So we'll save that. And now I want to shift gears a little bit, but these two things are really closely related, and we'll see really how closely shortly. So we have this list A, and we saw that we have things like in Python we have all of these functions that we can call. Like we can say things like sum of A, which is a function that takes an argument, which is a list, and computes its sum. And we've just defined a bunch of different functions that all take an argument, which we assume is a list for most of these, and does various things to them, changes the list or computes a list of the same length, whatever. But we've also seen sort of another way of calling functions on lists. And we've seen, for example, although I won't do anything interesting here, you can sort a list. And notice the difference in syntax here. On one, we called a function whose argument was a list. And here we did this weird thing where we took the name of the list and we said dot sort. So we called some sort function, but like referring to the list. Okay? That's because lists are, so Python is an object-oriented language, and lists are objects. And every object has things that you can do to it. And one of the things you can do to list objects is to sort them. So those are called member functions, or sometimes called instance methods of the object. So what we'll look at now is how we can define our own objects, and we'll see how all that fits in with equality and identity and this memory stuff. So let's open. So I want to define a new kind of thing. And let's imagine some really simple, let's do something really simple. And let's say the thing that I want to define is supposed to represent a person. So maybe a human being or just a person. So in object-oriented programming, you tend to choose what the things are you want to have, and then you determine what kind of attributes those things have. So what does a person have? What do you have? What's that? An identity. More specifically, a name. And even more specifically, names, like a first name. We tend to break them up. First name, last name. In some countries, there's also middle names. Anything else that a person has? Nationality. Anything else? Gender. We'll stay away from assigning genders to our persons in this class. It's a little dicey these days. What's that? Age. What else? Feet, hands, lungs, teeth. Not everybody has all of those things, but so a person has a lot of things. In fact, I mean, a person really is just a whole pile of stuff and attributes. So we have to boil it down to, well, what are the attributes of a person relevant to what it is we're trying to do? So if we're trying to maintain a student database, maybe a person has like a first name and a last name and an ID. or a first name and a last name and a student record or something. But let's, for this purposes of this class, let's just make person a really simple thing, just has a first name and a last name. Okay? So the way you define a new class like this is you just use the class keyword and you say the name of the class. In this case, I want a class called person. And almost inevitably, the first thing you define looks really ugly. And it's a function called init. And it always takes at least one argument, which is called self. And then it may take more arguments. And in our case, what I want is that when I create a person, then that person has a first name and a last name that's assigned to it at the time it's created. So I'll give two arguments, first name and last name. Okay. So I'll let you in on a secret, which is that in Python, every object is just really, underneath it all, it's just a dictionary. That it has values associated, or keys associated with it, and it maps those onto values. And everything about it is, everything about these objects is really, you can always think of it that way, and I'll explain how all of this works in a second. And notice that even in my my editor here, self got a different color than everything else here. And that's because self is usually reserved in Python to mean this particular object. So someone is, there's a special function called init. When you create a new instance of this object, this init function gets called with the arguments provided, and one hidden argument called self, which refers to this thing. And so here's a sort of classic looking init is I'll say this person's first name is equal to the first name that is provided in this argument. Okay? So this person's first name is equal to this argument here. This person's last name is equal to that second argument. Okay? So let's see if we've created something. Oops. So I just tried to create a person and something happened. It told me, yep, there's a thing called main.person and it's an object at some weird location. Let's do this a little more carefully. Let's say P is equal to that person. And indeed, P is this object at some weird location. Now, in this init function, I set two properties that are associated with P. I set its first name and its last name. So let's see if we can look at those. Yep, there's P's first name, it's Pat. And P's last name, Morin. Okay, so I've just created a new kind of object that a new class of objects called person, and every person has a first name and a last name that's assigned to it at the time it's created. Yeah? No, it's just that if I don't assign it to a variable, I'll lose it right away. So when I did this, yes, a person was returned and it was somehow shown to me, but I didn't save it anywhere. But there's nothing I could have said, what is that person's first name? And indeed, it tells me what it is, and what is that person's last name? That works too. But every time I do this, I'm getting a new person. In fact, we can check that. Because one of the things in this otherwise uninformative display of a person is this weird thing over here. And this weird thing over here, it says person object at something. Well, this thing is actually a memory address. And notice that each time I create this person, even though they always have the first name Pat and the last name Morin, this memory address keeps changing. So really each time I do this, I'm creating a new person off somewhere in the heap, and each time it's at a different location. So already that's telling us, for instance, that I can create two people. Let's say I already have P, and then I can say Q. So there's P, there's Q. Yeah, they're at different locations. There's a difference right there. This is a D and this is a 6. So I know if I say P is Q, are they identical? That's false, because they're really, the picture looks like I've got a person whose first name is Pat and whose last name is Morin. So this is a box. With this person, there's a box called first name, and there's another box called last name. That's over here. And over on the stack, P points to that thing. And off in memory, there's a whole other person with a box for the first name and a box for the last name. And that on the stack is referred to by a box called Q. Okay. All right. So we can we can just check that our understanding of that picture is really, it's really happening the way we think it is, because there's P's first name, it's Pat, but let's just change it. So now P's first name is changed to Pedro, but Q's first name is still Pat. So what that did is it went to P, went to their box called first name, created a new string called Pedro, and changed that thing so that instead of referring to Pat, it refers to Pedro. Has no effect on the person that Q refers to. All right. Okay, so I don't like the way that these things are these persons are being shown to me. And so in particular, I don't like this thing here, this way of displaying a person. And the other thing that's not so interesting is if I try and convert a person to a string, well, I get that thing as well. So there's a whole bunch of special, weirdly named functions or methods that you can override for objects that control things like what happens when you convert them to a string, or what happens when you try and add two of them together, or what happens when you try and inspect one of them. So one of those things, and all of these really special things, they all have the same weird-looking names, which start with 2 underscores, str, whatever the name of the thing is, and then 2 more underscores. And they take an argument, in this case, only one argument, which is the object itself. And this is the function that will get called if I try and convert this person to a string. Now, what it's supposed to do is return a string that represents this person, something that's maybe meaningful if the user decides to print this person. So let's see what that would look like. Well, I mean, a sort of natural way to represent a person is by their first name, a space, and then their last name. It's not the only way. Sometimes you might want the last name and then a comma and a first name, but let's be sort of informal here. And see what we've accomplished. So now I've created this person P. If I look at it, inspect it, it still looks strange. But if I convert it to a string, then I get a nice looking string. And if I print it, well, the print function converts things to strings before printing them, so I get a nice representation of this person now. Okay? So I said that there's a whole bunch of these magic functions that look weird like this with these 2 underscores before and after their name. Another one is called a repr, which is for representation. And it's the thing that controls what it looks like when you inspect one of these things, like we've done here. This is still not a terribly informative thing. If I try and inspect one of these persons, what I would rather have is something that really shows me maybe the contents and how to create it. In fact, what repr is supposed to do is it's supposed to give you a string which is valid Python code for creating this object. And in this case, to create a person, well, I know how I created this person, right? I called this function-like object with these 2 arguments. So I'll return a string, which is looks like that. And now we see that when we inspect these things, we get something nice, but not quite correct. The characters in this string should be quoted, because this is not valid Python code. That's better. Okay. So when you define your own objects, usually that's sort of the first couple of things that you might do, is define some conversion to string because it really helps with printing things, and some version of this repr function because it really helps with debugging and looking at things. It's not strictly necessary, but it's helpful. So, all right, so here's P, this person Pat Morin, and now I'll take Q to be a person Pat Morin. There's P, there's Q. Do you think P equals Q? But equals is supposed to say that they're equal, not that they're exactly the same thing, right? We had arrays at different locations that were equal. Is the one that's supposed to tell us whether they're the same, referring to the same thing, and of course they're not here. On the other hand, if I define Q equal to P, then P is equal to Q. And in fact, P is Q. So somehow there's this test for equality that, at least with this object, it doesn't help if all of this, they have the same first name and the same last name as it stands. In fact, right now, the only way that two persons will be treated as being equal is if they're actually referring to the same thing. And that's because equality in Python, this double equals operator, is really just calling a function. And it's a function that's defined for the object on the left-hand side of this operator. So, and the function is called, it won't be a big surprise, underscore underscore EQ. It takes an argument self, like all of the other things, which is the object that we're working on, the object that we're referring to. And it takes a second argument, which you can call whatever you want, but I'll call it other. So I get to define, when I define an object, what it means for two of those objects to be equal. Okay? And I think a natural thing for this very simple person class is to say that these two objects are equal if they have the same first name and they have the same last name. There's not really any other distinguishing characteristics. So, and what does that look like? Well, if they're equal, then if and only if my first name is equal to the other first name, and my last name is equal to the other last name. Now the first name and last name are strings. It's well defined what it means for strings to be equal. That's defined actually inside the string class. And now I'm defining what it means for two persons to be equal. And that's in the person class. So let's test that out. So P and Q really are different things, but now they're treated as equal. And that's just because when I use this equality operator, the only thing that Python is doing is it's taking the thing on the left-hand side and it's calling its EQ method. And for these objects, you can define methods of any name that you want. The magic ones and there's a good list of them that we'll take a look at, always have this double underscore, some name, double underscore. But you can do, other things like I can write a method called print yourself, and they should always take an argument, and the convention is that the argument is called self, and refers to that thing. And so here, let's say, how will this work? Well, it just calls the print function on this person, and the print function, we know, turns this thing into a string, and then prints that string. So it prints itself, doesn't return anything. Okay. So you define these objects, you can define these methods on them. The way you call the method is just by saying whatever the variable is that holds the object, dot the method name. And when you define the methods themselves, they're always taking one extra argument, first argument, which is the object itself. In fact, all of this is really just window dressing around something that I think we could do ourselves. Inside the person class, there's a thing called print yourself, and its first argument is q. So that'll do the same thing. So this q.printYourself is just a shorter way of saying, in the person class, called the function print yourself with the first argument being equal to q. In fact, you hear a lot about object-oriented programming and what a great thing it is and what a big deal it is, but really, a big chunk of object-oriented programming is just hiding the fact that there's this other notation of calling functions where you hide the first argument. It's just the thing that's on the left-hand side of the dot. Okay. So in this case, q is the thing on the left-hand side of the dot, and really that just means you're calling a function called print yourself that takes a hidden argument that includes q. Okay. So I think right now is probably the optimal time for you to go and do assignment 5. You could probably be done in an hour or two if you do it right now.